Okay, this is lecture 4. In lecture 3, we talked about electrons in free space. And after that, we look at how electrostatic potential barrier will affect electron propagation in free space. So we had this concept called tunneling. And then after that, we try to confine electrons in different environments. So we started from a quantum box in which electrons confined in one direction, but it's free to move in the other two directions. And then, quantum walls here. And after that, we try to add the confinement in the second direction. And then we have the quantum wire. So in this case, electrons are only free to move in one direction. And eventually, we confine electrons in all three directions. And then we had this quantum box or quantum dot concept. And after that, we talk about another very important concept in solid-state physics that basically is density of states, right? And then from here, we understood that electrons basically try to fill up the entire K space or energy space from the lowest energy first, and after that they end up at the highest energy, which is called Fermi energy. And then since the energy is dependent on the wave vector in the parabolic form, so eventually you end up at a spherical surface, which is called a Fermi surface. And then below the Fermi surface, so all the electronic or electron states are completely filled up, and above Fermi level or Fermi surface is empty. So this basically is in the low temperature or absolute zero temperature. And at a finite temperature, and of course, there's a finite probability for electron to occupy the states above the Fermi level or Fermi surface. And then at the same time, you have empty states below the Fermi surface. And then we will use this concept when we talk about carrier concentration, and also basically we talk semiconductor statistics, right? And then we'll use this Fermi-Dirac distribution concept. So now, before we talk about the semiconductor, we need to understand what kind of material will be a semiconductor, and what kind of material will be a metal, say for example, right? So to this end, we need to learn another very important concept we call energy band structure. So this is what we are going to talk about today. So I will just use one slide to summarize all these key concepts to give you an overview of how we end up at a material with a band structure. All right. So we have been talking about solid in this module, right? And then typically for solid, they have crystalline solids and then amorphous solid, right? And for semiconductor, we focus on crystalline solid. So this means that inside this semiconductor, you can see that atoms are arranged in a periodic manner. And of course, a different type of semiconductor, we have a different type of lattice, which we learned in the first lecture, right? Now, and so in the last lecture, lecture 3, we introduced the concept of quantum mechanics. And then, for example, if you have isolated atom, and then inside this atom, you have a nucleus, which is positively charged. And then, of course, you have negatively charged electrons, which are moving around this nucleus. And then from quantum mechanics, we understand that electron cannot take a continuous orbitals. So electron can only take this kind of discrete orbitals. And then at each orbital, and the electron will have a different energy. So this means that energy are also quantized. The isolated atom is the so-called perfect quantum confinement environment. So since those electrons only interact with themselves and also the nucleus, so the energy level is actually very, very sharp, right? So in principle, you just you can consider that there's no spreading of this energy levels. It's just you have a single value of energy level, right? However, if you have another atom which comes close to this atom, and of course we're talking about inside solid, and then so the electrons from two atoms will try to interact with each other. When the electrons interact with each other, it means the wave function will overlap with each other. So in this case, from quantum mechanics, we know that the consequence of this interaction is a broadening of this energy levels. So this means that if you really only have two the two electrons, and in principle, so after interaction, this single energy level will split into two. However, if you have more, and then what happens that, and of course, and then once you have an interaction, and then this will split. So eventually, you end up like something like energy bands, right? So of course, to form energy bands, and then we need this kind of periodical environment. So now we come back to this the real situation inside crystal, and of course what you have not just two atoms, and you have many atoms, right? And so here I just show a one-dimensional crystal. Of course, typically a crystal is three-dimensional. It has a three dimension. So this means that each the electrons inside each atom will interact with many other electrons, surrounding this atom, right? Now, for this crystal, I remember last week, in lecture 3, we actually start from free electrons first, right? So we get free electrons from the atom. So we try to excite electrons inside atom. So if the energy is high enough, and then we should be able to make electrons escape from the interaction of the attractive force of the nucleus. So, and then, so free electrons, of course, and from quantum mechanics, we know that, so the wave function of free electrons are the plane wave, right? And then from this plane wave wave function, we try to apply this periodic boundary condition, and then we find that, so K is quantized, and then by using this concept, and we have basically derived this Fermi energy from the surface, and also density of states, right? This was what we have done in lecture 3. Now, we come back to in this lecture, we look at, again, we look at the periodical electric potential, but now this is not some sort of water, periodical boundary condition like the one we talk about here. Here, we have a real periodical electric potential from the real lattice, right? So when we have this, and so now the difference between this case and this case is that so in this case we don't have a periodical electric potential. Basically, we only apply a periodical boundary condition. In this case, we have a periodical electric potential due to the lattice itself. So so once you have this kind of environment, of course, electron is not free anymore. So this means that you cannot just have a simple plane wave as the wave function for electrons. Now we have a very important concept here, and so this actually is a theorem. And so basically, people have found that in this case, the wave function will have a certain form, and which somehow you can see that it's derived from a plane wave that is different from the plane wave, right? And so this is something we'll learn first today, and then from pure lattice, I remember in lecture 1 and 2, in lecture 1, and so once we have a periodic lattice structure, and then we can define the reciprocal lattice. And then from a reciprocal lattice, we define the first Brownian zone. So first Brownian zone basically is the primitive cell of the reciprocal lattice, right? Wigner seed cell, right? So, and then for Brownian zone, I remember I mentioned that we are only interested in the first Brownian zone. And so what happens that when you have this kind of reciprocal lattice, and then this will interact with this electron wave, and the electron wave will be reflected at the Brownian boundary, okay? And just like a phonon, a less vibration, which is reflected from the Brownian boundary, and then you basically form this something like a standing wave, right? The same thing will happen in the case of electrons. So electron wave will also be reflected at the Brownian boundary, the first Brownian boundary, and this will give you a standing wave. So when this happens, and then you will have this kind of electronic band structure, which is extremely important. So this means that instead of this discrete energy levels in an isolated atom, inside a crystal, and at a very deep level, and you still have a quite so-called sharp, quite close to a single atom like the environment. This means that you have a very sharp discrete energy levels here. However, and those levels, we are not interested in those levels because those levels are already filled up by electrons, right? So that's cannot move. And then we're only interested in the ones which are near the Fermi level. And then those which are near the Fermi level and will be somewhere around here, right? So then you can see that you do have this discrete energy levels at the deep. Fermi, this is not the Fermi C, okay? It's far away from Fermi C. And we call basically core electrons, right? And but for valence electrons, you see that they will form this kind of energy band, right? So, and the energy band will have different we have different types of energy band, and some of these will give you metal, some will give you a semiconductor, and some will give you an insulator, right? So this is what we'll learn today. So that's why today we'll start from here first. Okay. So we'll not prove this, but we just take this as a theorem. So this is called Bloch's theorem, right? So basically, what this Bloch theorem says that so electron inside this periodical potential of a real lattice, and we'll have this kind of form, right? So you can see first of all, cosine. We still use cosine to represent wave function. And then, so right-hand side, you can see we have this is a product of two terms. So the first term, you can see this is exactly the plane wave we use to describe free electrons, right? The plane wave. So it means that the wave function of a free electron is given in this form, right? And then we, in addition to this, have an additional function, additional term here. So this is due to the presence of periodical electric potential, right? So this U is a function of R. R is a position variable, all right? So of course, this is the function of K and R, okay? So now, we'll talk about K later, but anyway, you can just assume that K is just still the wave vector, right? So with electron in a wave vector, okay? So now we have two, this index here. So one is N and the other is K, right? So what does N mean? So N indicates, so it's given here, is the index of energy band. So just now, if you go back, you'll see that we can have this different energy band here, right? So you may call this, for example, N equals 1, and then the next one will be N equals 2, and this will be N equals 3, N equals 4, and N equals 3. So it just indicates the different energy bands, okay? And then for each band, for each energy band, and then of course you have the K can change within a certain range. So basically it's from a center of the Brillouin zone to the boundary of first Brillouin zone, okay? And so, and then you can define your EK dispersion, remember. So all the way you have talked about EK dispersion, right? So the EK dispersion for example, in quantum well, when we talk about the EK dispersion, and then we have a different mini energy bands, right? And then for each band, and then you have a EK dispersion. It's the EK dispersion. And then for this real crystal, it's the same. So we have different energy bands, and then for each band, we have a EK dispersion, all right? And by right, there should be another one, which is not given here, called sigma. So sigma basically is the electron spin. So for magnetic materials, it's very important. But for semiconductor, anyway, we just ignore the first, right? So that's why, in principle, you should be able to specify, once you specify N basically tells you which energy band you are talking about. And the K basically tells you if you can find an EK dispersion for that energy band, and then basically you know how electron will move inside that crystal. And sigma basically is the electron spin, which we just ignored here, okay? So now this U is not somehow you just put a function here. This U actually satisfies this relation. This means that U has the same periodicity, right, of your lattice. So if your lattice, for example, in certain direction, the lattice spacing is the translation vector, fundamental translation vector, right? Or you got translation vector of the crystal is T, and then so you have so when you shift R by T, and then so this U is still the same, and for the same NK, right? So this means you have same periodicity of the lattice. Okay, so that's why if you look at this wave function, so basically, so if this part is a constant, so this means that if the electric potential is negligible, right? And then so basically you get a plane wave. Okay, so however, if the electric potential is finite, and of course the electron will feel the presence of the electric potential. And then if the electric potential has a periodic distribution, and then you have a U here, but U will have the same periodicity of your electric potential, right? So just to show you what happens in real data, this just as a sketch, right? So basically you can see that, so this will be the electric potential distribution. Okay, you have a certain periodicity, all right? And then, so this is the plane wave, this is for free electron, right? And then you have this U. So U has the same periodicity as your VR, right? So this U, basically you can see that it changes frequently near the nucleus. So basically you can see that this is due to a Coulomb interaction between electrons and nucleus, right? So Coulomb interaction is the strongest near the nucleus. So that's the reason why you have this fast oscillation. And then between the two atoms, of course, the interaction is weaker. And you can see that U is almost a constant, right? And then so this UR multiplied by this plane wave, and then you get this this wave. So this is basically, it sounds like a plane wave which is modified by this UR, right? So if we superimpose this U here, you will see something like this one. Okay, so now you can see that in between between the two atoms, so this wave function is quite close to free electrons, right? And but near the nucleus, near this is the nucleus here. Okay, so near the nucleus, you can see that the wave function is quite different from this plane wave, right? So this is the picture you should have. Okay, so now, and so what's K? So this is a very important concept here. And for plane wave, you know that the K basically is a wave vector, right? And so, but here, this K is still the wave vector of electrons, right? But the only difference that in the free electron, and then you multiply this K by H. So HK basically is a momentum of free electron, right? So this is basically for free electron, we already derived it, and so the momentum by HK. And so here in real lattice, although K is still the wave vector, but HK is not the momentum of the electron anymore, not the real momentum of the electron. This means the real momentum means that we just compare with free electron, because in free electrons case, HK is a real momentum of electron. But in the lattice, inside a crystal lattice, and the HK is no longer the real momentum, true momentum of electron. But we still call this a momentum. So what this we call crystal momentum. So first we explain why this is not the true momentum of electron. So in quantum mechanics, we talked about in last lecture. So if you use a momentum operator, right? So this momentum operator, of course, is the electron momentum operator to operate on this wave function. And then so you see what you have. So so the momentum operator basically is H divided by I del. So that's a momentum operator, right? So and then use this one to operate on this. So H over I is a constant, just put it here. And then del is del operator, right? And so this wave function, we just use this Bloch's wave function. Bloch's wave function. This means that you have a plane wave. The plane wave modified by this U, which has a same periodicity of the lattice. Okay. So now so this is a product of two functions, right? So we can always try to use this del to operate on this one first, and then leave this one and there. And then if you do this, and then of course you get a IK, right? So I cancel out, and then you have a HK. So basically you have HK and then this psi. So you get back, right? Because after you differentiate this one, you find a gradient of this one. So I hope you understand this, right? So if you, just in case students, maybe I just right here so that So remember del, and it's the operator, right? So which is given by so partial x, and then partial y, and then partial z, right? So that's why del e to the power of I k dot r. So this basically is given by, so when you differentiate this one with respect to x, and then you get I k x, and then after you get I k y, and then I k z, and then you still have this I k dot r here, right? So what this, so this of course is this one itself is ik, right? So it's right here. So it's ik. So that's the reason why you get ik. So and then this I is cancelled with this I. Okay, so just go back to my little pointer. So and then so you can see that eventually, so this I, right, will cancel with this I, and then you still have this one multiplied by u, and then you get back cosine itself. Okay, so that basically is this one. And then next, since this is you need to use the product rule, right? So next you need to find the gradient of this one, but leave this one here, right? So that's why we just have this one here, and HOI is a constant, and the gradient of this. But the gradient of this, since we don't know the exact form, the closed form of this u, so we don't know how to find out the gradient. So we just leave it here. So now, reversely, you can see that and this p operator, so the momentum operator cosine, is not equal to this one, right? Because this is the one. So because there's additional one here, right? So only when this is 0, and then so this term will be equal to this one, and in this case, basically hk is the true momentum of the electron. So under work condition, so this will be 0. This means that u will be constant. If u is constant, and then of course you go back to case that if this is a constant, and then this wave function basically is a plane wave, right? So it means that only when you have a free electron, this means that you don't have any periodic electron potential, and then this hk is the true momentum of your electron. It's basically electron momentum. And however, if this is not equal to 0, this means that in real lattice environment, this is not equal to 0. And then this p operator, the eigenvalue of a p operator will not be hk. So this means that hk is not the momentum, electron momentum, right? And however, in solid state physics, people find that this hk, although it's not the electron momentum, but we still can, they still have the the property of a momentum. And then by using this, we can simplify many issues which involve the interaction of electrons and the phonon, electron and the photon, right? So this is called crystal momentum. It's a crystal momentum. So it's in here. Okay, so this is a very important concept. So this basically is called crystal momentum, right? So it's something combined, something like a combined momentum of crystal and the electrons, right? So this, I mean, it's a little bit difficult to understand, but they try to realize that if you really use the momentum, true momentum of electron, and then this will make all the discussion very complicated, right? So what we do that we just put this crystal environment together with the momentum of electron, and then we come up with something in a very simple form. It's still hk, but it's a crystal momentum. Okay, so why this crystal momentum is so interesting? That's because that people already found out that when you have a free electron, right, and then the free electron interact with the photon, for example, and then of course energy and the momentum have to be conserved. So the momentum conservation basically we're talking about momentum transfer between the electron and then the photon. And however, inside the crystal, and then what happens that we don't need to talk about the momentum transfer directly from electron to photon. That would be very complicated. Why this is the case? Because electron is not the plane wave anymore, right? So however, if we define another momentum, hk, we call crystal momentum, basically it consists of both the electron and also interaction between the lattice and the electron. And then we find that the interaction can be described by momentum conservation between this HK, which is crystal momentum, and the particle, which we are talking about, for example, maybe a phonon or photon, right? So that's why this is very convenient, okay? So when we talk about the electron scattering inside lattice, so basically, when we talk momentum conservation or momentum transfer, then we use this HK. And another very important concept is that, remember, if you have a free electron, right? And then when the free electron is stationary, and then if you apply electric field, of course, you'll start to move electron in a certain direction, right? And of course, when the electron is stationary, when you apply magnetic field, nothing happens. And however, in general, when the electron is moving, and then you apply electrical and magnetic field, and then your electron will feel two types of forces, right? So the first one is called electrostatic force. Basically, it's a minus E. So minus E is the electron charge and multiplied by electric field. And of course, if your electron is moving, and then you still have this so-called Lorentz force, right? So if you have a free electron, and then what do you have? You simply have a velocity cross the magnetic field, right? And however, in quantum, in this crystal lattice, what people find that now we don't use crystal momentum. Sorry, we don't use the electron momentum. We use crystal momentum here. So if we use crystal momentum, and then we find that the change of this momentum with respect to time is still governed by this equation, and the first term is the same. So this is the external electric field. And then, so this term, this V, basically, since electrons weave inside this crystal, and then it's the group velocity. So the group velocity comes from EK dispersion. So that's why later we'll talk about the energy band structure. So once we know the energy band structure, it means that we know EK dispersion, and then we can calculate the group velocity. So once we know the group velocity, and then we put here, it just still Lorentz first, right? But now this is not electron momentum. This is a crystal momentum, right? So this makes sense is because that this E is the external electric field. The B is the external electric field. So if you really change this one to electron momentum, now what happens? This should include both external electric field and whatever internal field due to other electrons or nucleus inside the crystal, right? If you do that, the whole thing becomes extremely complicated, right? So this means that by introducing this crystal momentum, and then this so-called electron dynamics in electromagnetic field, so electromagnetic field become much simpler, right? So that's why it's crystal momentum is a very important concept if you want to understand the electron dynamics inside the crystal. Okay, so as I explained, if you use a real electron momentum, this will become very complicated. Okay, you have to take into account both external and the internal electric field and the magnetic field. Okay, this is what we don't want to do. Okay, so so these are the important concepts about Bloch theorem and then crystal momentum. And then we look at electron band structures. It means why some materials are metals and some are semiconductors. So in order to do this, we look at a very simple periodic electric potential first. So this is basically it's described in almost all textbooks of solid physics and semiconductor physics. So this is called Kronig-Penney model. So what this? So in this model, so we just assume that we have this kind of periodic electric potential, right? Yeah, a one-dimensional periodic electric potential in real space. And so this the potential has a barrier of barrier height of V0, and then between each barrier you have a region called well. So this width is A, and then the barrier itself has a width of B. Okay, and then we assume that the electron is moving in the x direction, right? So it's a one-dimensional problem. And then we'll try to understand, so basically find out the EK dispersion. So remember, we always try to find out EK dispersion for electrons. So once we know EK dispersion, and then just now we can find out group velocities, for example, right? And of course, we can find out effective mass, right? So once we know all this, And then when you apply electrical and then magnetic field to the semiconductor, and then we'll know how electron will move. That basically is our purpose, right? So why do we need to know how electron will move in the semiconductor? Because we want to use semiconductor to fabricate the device. What kind of device? It's a device in which we can control the electron movement. So why do you control electron movement? Because you want to realize certain functionalities. For example, you want to turn the electricity on and off. Basically, the switch is the most important device. And then you want to amplify in a signal, right? So for all these basic operations, you need to understand how electron will move inside the material, right? So the best way to control the electron movement, of course, is electric field. And then, of course, you can also apply magnetic field as well, but the electric field is still the best one, okay? So to understand this, and then we need this to understand EK dispersion. So the EK dispersion, to find out this, is basically we need to use quantum mechanics, right? So what do we do that we just try to write down the Schrodinger equation for this system. So the Schrodinger equation for the well region, so basically given by this, that means that the reference of our electric potential is 0, right, in the well region, right? And then in the barrier region, of course, will be the V naught, right? So, and then in the barrier region, so this will be our Schrodinger equation, right? So with the Schrodinger equation, and then we can try to write down to the wave function. But here, since you have a periodic potential, so the wave function must satisfy this Bloch theorem, right? So this means that from Bloch theorem, we know that this wave function must have this form. So this means that the wave function, so for example, in this region, so what this region, this is from A plus B to 2A plus B. So basically it's this region, right? So A plus B, so this one, to 2A plus B, basically this one, right? So that basically is the wild region. Let me see. And A plus B, so this is A plus B, and this will be 2A plus B, right? So this will be 2A, right? So basically this region. So the wave function, this region, so that basically is this one, must be related to the wave function in this region by Bloch's theorem. Why? Because from here to here is one period. And of course, from here to here is also one period. So the period is A plus B. So based on Bloch's theorem, so this must be, just look at this, this is Bloch's theorem, right? So this means that when this R change by the periodicity of lattice, and then this one will not change because this one has the periodicity of your wave function, right? And however, so this one, when R change by, say for example, A plus B, and then of course you have an additional phase K multiplied by A plus B, right? Because the one-dimensional case, you don't need the top product, just multiply. So that basically this one, right? So this means that the wave function in this region multiplied by this phase factor will be the wave function of this region. So we directly follow this Bloch theorem, right? That's because this one does not change if you go by one period. Okay, so that's given here, right? So the T is A plus B. The T is A plus B here, right? And similarly, the wave function in the barrier region, so from A to A plus B, so that basically this one, within this region, from A to A plus B, must be related to the wave function in this region. All right, minus B to 0, and by this phase factor. Okay, so the same phase factor. So this is what what we have, and after that, we will solve this, substitute this into the Schrodinger equation, and then at the Schrodinger equation, we will have this. If you look at the Schrodinger equation, basically you have this solution. Sorry, we don't substitute this one yet. Okay, we just look at Schrodinger equation from previous Schrodinger equation. If you solve it, the general solution will be given this. So in the wild region, so you have this standing wave. All right. So this basically you have wave propagating. Sorry, not necessarily standing wave yet. Okay. So you have two waves. One is propagating from left to right, and the other one is right to left, right? That's because that no matter where the electron come from first, and so suppose it initially propagates in from left to right, and then after reflected, and then you get the one propagating from right to left, right? So if it's initially from right to left, and then after reflected, and then be from left to right. So anyway, you have two terms, right? So of course, in the B are coefficients. So alpha from the previous slide from Schrodinger equation, I'm sure you should be able to find out this one. I've been using this one for many, many times. And inside a barrier, so because we are interested in energy which is lower than the barrier, so this means that the wave of decay, again, you have two waves. It's one from left to right, another one from right to left, and then both will decay, right? So that's why you have this, okay? Now, once you have this one, and then we look at the boundary condition. So the boundary condition, basically, we still have two boundary conditions. So at each boundary, the wave function must be continuous. So that's why we look at the first boundary is at x equals 0, right? So this boundary. And then we have two boundary conditions. So phi is continuous at x equals 0. And then also the first order derivative, right, continuous at x equals 0. So we just try to use basically, this one and this one, all right? And then the other one is you differentiate this one, differentiate this one, right? So you get this two. Okay, I hope you can do this by yourself. So that's why I will not derive it. Anyway, it's very simple, right? So the next, you can see that this psi must be continuous at x equals a as well, right? So this is another boundary, right? So now you can see that so at x equals a, and of course the psi from y is given by this, right? And then the psi from this barrier, and then you have to read it to this one, right? Read it to this one, because this is the one we solved here, right? So by a phase factor, which is this. So this is simply get from here, right? So now you can see that so this is equal to this one, and similarly, first order derivative must be continuous. And so again, you have this phase factor. Okay, this is due to Bloch's theorem, right? So now you can see you have 1, 2, 3, 4, and then 4 equations, and then 4 unknowns, right? 4 unknowns. So, and of course, this is a very simple simultaneously equations, simultaneous and also homogeneous equation, right? So what do you do that? You just bring all the terms to the left, and then the coefficient for the right part will be 0. And then you require the determinant of coefficient matrix of the left-hand side to be 0. And then if you solve it, and then you can basically find that this is the solution. All right, it's not a real so-called analytical solution, but anyway, this is the maximum you can go, and this is what you have. All right, so this means you have to find a way to again maybe use a graphic. Of course, you can use computer solve it numerically. It's very easy, but in order to understand the basic physics, and then it's always good to look at some extreme cases and then use the graphic method to solve it, right? So now, if you look at this equation, so you can see that you have basically left part and the right part, right? So at the left-hand side, and if you examine these two terms carefully, you see what you have here. You have beta alpha, and then of course here you have beta alpha and then beta alpha, and then in addition you have A and B. And anyway, A and B are given, right? Because this A and B basically define the well and the barrier width, right? And then beta, remember, inside the beta, and it's given here. So you have energy and then barrier height. So barrier height is also given, right? M is a mass, suppose it's given, and H Planck constant. So this means inside beta, the only one you unknown basically is E. And also for alpha, with the alpha, the only unknown basically is E. right? It's energy. So this means that they have energy here and energy here, right? And if you look at the right-hand side, then A and B are constants, are given. The only unknown is the K. So this means in principle, what's this equation? So this equation, if you solve it, basically you can find the EK dispersion. The energy is a function of K, right? That's what you have to do. So, but obviously this is difficult to solve. That's why we try to simplify this a little bit by looking at some very simple situation. So in our situation, we consider a case that we have this kind of periodical delta potential function. So what does this mean? This means that we let B approach 0. Okay, let B approach 0, and then you only have this delta electric potential. The height is still V naught. Okay, but if V naught is finite, and then you let B approach 0, and then you get a free electron, right? Right. So basically, because V naught is finite, and then B is 0, so you go back to a free electron case. And however, we try to, but that would not be very interesting, right? So what we do that we'll try to increase V naught. So we assume that the V naught approach infinity, and then the barrier width approaches 0. However, the tool will approach in such a way that this term itself is finite. Okay, so what this? Then we try to look at this one. So we just write this one here. Sorry, what this? And so we will not do this. We'll just come. Okay, so now, so what we do that we'll just try to. If you look at beta square, so the beta square, so it just derive from here, right? So you can see that the beta square, so basically is 2m, and then V naught minus E squared, right? And then divided by h squared. And then multiplied by BA, so basically it will be BA. Okay, and then divided by 2. So divided by 2, basically this. All right. So basically, we look at this, and so if 2 basically cancel out, right? And then so we rearrange this a little bit. So we have m, so A, okay, and then h squared, okay. So now inside we have V naught minus E, and then we have B. Okay, so now if, of course, this will be a constant, a finite constant. And then since we not approach infinity, so this means that we can ignore this E because E is very small compared to V naught. So eventually this will be V naught B, right? So this means that what we are trying to do now is we assume that so B will approach 0, V naught approach infinity, but the product of this is finite, right? And then multiplied by this constant, we call it P. So this is what we want. We want to do. Okay. If this is the case, and then of course in this case you can see that this beta is much larger than alpha. Why? Because alpha is given by this one, and then beta is mainly determined by V naught, because this is very small. So V naught approaching infinity, of course, beta is much larger than alpha, because E is much smaller than V naught, right? And then, of course, this beta B will be much smaller than 1. Why? Because beta itself, so you can see that beta square, so beta square B, so basically this one, right? So beta square B is V naught B, right? And then this is finite. And then, of course, beta B basically is a rho square, right? So this is on the order of beta B is on order of rho square V naught B. So that's the reason why if this is finite, and then this, of course, is much smaller than 1. Okay. So if this is the case, and then this left-hand side can be simplified to this, right? So why this is the case? That's because that sin HB, so sin HBB, beta B, basically simply be given as beta B, right? So when this is small, okay. So you can try to do it by yourself. So it means that this is equal to beta b. So this is beta and this are cancelled out, right? That's why you have a b here. Okay, so then you have b and then beta square. Okay, so that basically is this one. All right, that's what you have. And then so alpha a is still here. So you have alpha and then you have a. Okay, so anyway, you just try to substitute all this in, and then you should be able to get this one, and then plus this one. So when this is very small, of course, this will be 1, right? This cosine hedge will be 1. Okay, so this I hope you know what's this cosine hedge function and what's sine hedge function, right? So cosine hedge basically is e to the power of beta b plus e to the power of minus beta b divided by 2. And sine basically e to the power of beta b minus e to the power minus beta b divided by 2, right? So that's why when beta b is very small, and then this basically is 1, the whole thing is 1, okay? And then you have this one, right? So, and then you have this. And then of course here, when p approaches 0, you only have a here, right? You only have cosine a here, right? So now, if you look at this equation, we still need a graphics method to solve this. But at least this equation becomes very simple. So now we only have k here, and then E, the energy, is only contained in alpha. So because alpha will have E, that's why we don't have beta anymore, right? So that's why you only have E energy here, and energy here, and energy here, all right? So now, so to solve this, and if we use the graphic method, and then we can find that, so this is the equation. I just rewrite this right here, all right? So if we sketch out the left-hand side, so that'll be given by this, okay? You can try to do it by yourself, that basically this one. Okay, so now reversely, you can see that, so this function and is not always between 1 and minus 1, right? And then in certain regions, so the value actually is beyond minus 1 and 1, right? Smaller than minus 1 or larger than plus 1. So this means that for that region, and then you only have a solution for this equation, because the cosine Ka can only take values between minus 1 and 1, right? So that's why we just draw 2 lines. So dotted line, one here and the other here, okay? And then, so this is the function. This is we plot this one as a function of alpha a. So because alpha a is here, right? So now we can see that this equation does not have any solution in this region, in this shadowed region, because left-hand side is larger than 1, all right? So this means that you cannot have an energy. You cannot have an energy within this region. So why? Because you don't have a solution for this alpha A, because E is contained in alpha A. So this means that the electron cannot take energy, within this region. Okay. So and then of course in this region, so what happens that so what happens to your K? And of course in this region, so when K itself, you can see that so that basically you can see from here, right? You can see from here to here. So that's the first region, and from here to here. And then although your K can change, right? Because the K still can change, but there's no solution for this equation. Means that the electron cannot take energy within this region. So this is energy, right? So now only when you reach this point, when alpha, because alpha A is changing, right? Because A is a constant. So only when alpha A reach this point, and then you can see that the value of the left-hand side will become smaller than 1. So in this case, of course, you have a solution for both E and K. So this means that now you can see this K will change from here to here, and then this energy will change, from here to here. All right. So it means that because from here to here, and alpha A is increasing. So when alpha A is increasing, energy is also increasing. But energy is increasing to very small amount. So once you increase to here, and then since this part is already minus 1, so that means that this Ka is already pi, right? So Ka changing from 0 to pi, so now here. So when you reach this region, and then again, you don't have a solution for K and E again. Why? Because within this region, you can see that the energy is increasing. So energy is increasing, but you don't have a solution for this. This means that you don't have a K which can define this electron, right? So this means that, or in other words, electron at this Ka value, and then the electron electron cannot have energy within this range, even when alpha A is changing. So this means that when alpha A, from here to here, remember alpha A is still increasing, so energy is increasing, but electron does not have that kind of energy, right, within that region. So that's the reason why you have a gap, and then you reach here. So this means that, so when you reach here, you can see that your Ka is still pi. Ka is not changing, it's still pi. So this means there's a gap. So once you come here, and then Ka can change again. So this means that Ka will change and the energy will increase. And this one. And however, when you reach this point, and then again, there's a gap here, right? So so energy will jump from here to here. And then, of course, K is still the same pi. It's pi here and the pi here. K is not changing. From here to here, K is not changing, right? That's why there's a gap here. So when there's a gap, and after that, we just continue. Okay. So now you can see that if for free electron, right? So roughly, you can see that this is quite close to a free electron. This dotted line actually is the free electron. So you can see that due to this periodic electron potential, and then energy cannot be a continuous function of K, right? And then at a certain Ka values, and then you have a gap. So this is a very important finding. Okay, and then so after that it'll continue, right? So now if we compare this with a free electron, and this is what you will see. So for a complete free electron, and then this is the EK dispersion. So when K is increasing, and then the E will increase in parabolic way, right? Because the E is proportional to K squared. Okay, this is free electron. And however, if you put this free electron into a periodical real electron potential, and then you get this kind of dispersion. Okay, and then you can see that the energy is discontinuous, and they have all these mini bands, right? So mini bands, and then for each mini bands, within each mini band, and then energy is continuous, is a continuous function of K. And however, at a certain K values, so basically all these are blue ransom boundary, right? So they will show this at the blue ransom boundary, and then a gap is opened. So this is called energy gap. Okay, it's a very important concept here. So now we need to understand why this is the case. So why this is the case? I think if you look at this one carefully, I think you already noticed that it's quite similar to monatomic chain lattice vibration in the monatomic chain, right? So we have Q and then omega, and then remember, so we have a so-called first Brillouin zone, right? So the pi over A here, and then so this is minus pi over A, and then remember, so we have something like this one, right? For monatomic chain, and then we talk about so what happened here that and here the group velocity and actually is 0. Why? Because you form a standing wave. This means lattice vibration wave is reflected Brillouin zone. And then if you look at the electron, it's very similar. So you look at what's happening here. All right. So let me back to the pointer. So you can see that. So what happens at here? You can see the bit, and also here as well. Right. So you can see that basically you have this so-called saturation of this EK dispersion, and then actually this is something like a local maximum, this local minimum. So of course, if you look at dispersion, so dEdk is 0, but dEdk, remember, is the group velocity of electron, right? So this means that so what happens at this here is because you have a reflection of an electron wave. Okay, so once you have a reflection, and then what happens that And you have both forward-going wave based from left to right, and then backward wave, the reflected wave. All right, is basically from right to left. And then these two waves will interfere with each other. And the interesting thing is that this reflection, it will give you two types of standing wave. So one type of standing wave is that during the reflection, the phase is not changed, okay? And then in this case, and then you simply have this one multiply this one, okay? Sorry, plus this one. And then you get one type of standing wave. And the other type of standing wave that actually during this reflection, what happens is that the phase is changed by 180 degrees. That means that you have this one minus this one, and then you get another type of standing wave. So what happened to this case, actually in quantum mechanics, although here we talk about reflection, in quantum mechanics in principle, if you have two wave function interacting with each other, you always have two type of combination in quantum mechanics which is allowed. So one is the two simply add up. The other one is one subtract the other one. Okay, and typically, and this one will give you a low energy because you have a overlap, right? So this is called a bonding state, and this is called anti-bonding state. This is in chemistry, in the terminology of chemistry, when you talk about chemical bonding, it's something like this one. But here we simply use this interference of two waves. So basic principle is the same. So then you can have two standing waves, one this one and the other this one. And if you sketch the probability of the two standing waves, and then you get two different situations. So the first one, so this is called the plus sign. So we call something bonding state, right? So bonding state, you know, that typically is a state which is with a lower energy. And then you can see that electron, this is a probability of electron is a maximum near the nucleus. Again, this is a maximum near the nucleus, maximum near the nucleus. So when this happens, and then this interaction will give you a lower electric potential energy. That's because that the Coulomb interaction, electrostatic energy. If you have two electron clouds, so one at the density of ρ1, the other ρ2, and then the Coulomb interaction energy is all given by this. Since it's an electron distribution, you have to do the integration, right, in the entire volume. So now, if ρ1 is positive and the ρ2 is negative, and of course the overall interaction energy is negative, so this means this will give you a low energy. So that's basically is for this bonding state. And the other one, something like an anti-bonding state or excitation state, higher energy state. So that basically is this blue one. And then the blue one, you see, so what happens that the electron density is lowest at the nuclear position, lowest here, and then it's a highest in between these two. So in this case, and of course, and so what you get a higher energy, right? That's because that the interaction which gives you the negative energy mainly come from this nucleus, and then but here, since this is electron density is very low, that's why even this is a negative, but it's very, very small. So eventually, compared to this case, energy will be higher. So that's why. So you have two different type of energies, right? So, and also the other way to look at this one, remember when we talk about this diatomic chain, you still remember, right? So the diatomic chain, so we have this one, and then larger one, the smaller one, larger one, smaller one. So, and then remember, when we talk about this one, we have a gap at the first Brillouin zone boundary between acoustic mode and then between acoustic mode and optical mode, right? So I hope you still remember. So if we sketch it, and then we see something like this one. Suppose this is a Brillouin zone boundary, right? And then so this is a acoustic mode, and then this is a optical mode, right? So of course we have another one here, and then so here. Okay, so so now this is omega, this Q. This is for phonon, right? So remember when we talk about this frequency gap here. So remember in quantum mechanics, frequency is energy, and it's frequency, right? Because they are proportional to each other. So when we talk about frequency band gap here, so why this of course at this point you have a lower frequency, and then here you have a higher frequency for the same Q value, is because we find out that here, so what happens that is the heavy atom is oscillating, but the light atom is stationary. Since the atom is heavy, so that's why the frequency is low. And then for this one, just opposite. It means that the small atom is moving, but the large atom is stationary. That's why I have a high frequency, right? Similarly, here you can treat these two cases. So this is minus sign plus sign, sorry, this blue and red, blue and red, and over these two waves as two type of atoms, right? And then so this atom, so because these are electrons, right? So these electrons, you can see the two type of electrons. So one is tightly bonded nucleus, and the other one is loosely bonded nucleus. So the one which is tightly bonded nucleus, of course, is difficult to move, right? So that's the reason why I have a lower energy. But this one, which is loosely bonded to nucleus, and then it's easy to move. That's the reason why you have a higher energy. Quite similar, to this kind of concept, right? So, and of course, one is for phonon. And phonon is, we are talking about a lattice vibration, the wave, lattice vibration wave. And the electron, of course, the electron wave, right? But overall, this concept, you can look at this as very similar, right? So why we have a band gap here? This means that you have some sort of electron distribution, electron standing wave caused by a Bragg reflection. And then this standing wave has a electron density distribution. And then this electron density distribution, and so the maximum of the electron distribution. And then for one wave is near the nucleus, and the other wave is in between the two nucleus. So, but the wavelength is exactly the same, or wave vector is exactly the same. And in fact, this will only happen when your wavelength is wave vector is at the Blue zone boundary, right? So only when this will happen. And so to sketch this, you can see that if your wavelength is very long, this means that your wave vector is very small, and then it means that you have not reached the first Blue boundary. And there's basically there's no difference between this blue wave and the red wave. Why? Because if you look at red wave and overall, so for example, look at this portion, right? It covers many, several, nucleus, right? And then you look at this blue wave, and also here it covers so many, nucleus. That's why averages are exactly the same. There's no difference. So that's the reason why no band gap. And then you can try to reduce this wavelength, and then even up to this case, and there's still no difference, right? So why? Because, for example, here this is the maximum, right, for blue wave, but here is the maximum for the red wave, right? So overall, look at the overall ranges are the same. There's no difference. So only when you reach this situation, then you see that. So what this situation basically, you can see that the period of the wave is exactly the same as the period of the lattice, right? So when this happens, and then so this is red, and then the blue will be different. Why? Because for red, and so if you look at this case, the red, the maximum is always between the color might not be, same as previous one anyway. See, the red is always between the nucleus, and the blue is always on top of the nucleus. So that's why these two set of a standing wave will have a different energy. But for all other cases, they're the same. So that's the reason why we only see the gap at the Blue zone boundary, right? So, and of course, and if you try to reduce this wave further, and then after you reduce to a certain condition, this means you reach the second Blue zone boundary, and the same thing happen again, right? But it only occurs at the Blue zone boundary. And then for all other K vectors, you can try to sketch out the figure by yourself. And after you average out, you'll see that there's no difference, right? Okay, so this basically, this is what you will see, right? Okay, now next we look at this we call this a reduced zone representation. This means that in principle, you can see you have this band gap at all Blue zone boundary, right? So this is the first Blue zone. Excuse me. This is the second Blue zone boundary, and then this is the third Blue zone boundary, right? So in principle, you can do this, but this, of course, is not very convenient, right? So, and then, so what we can do that we can, since all this electron states represented by this K vector outside the first Brownian zone is equivalent to one of the wave vector inside the first Brownian zone. So that's the reason why we can always try to bring or shift the energy dispersion in higher Brownian zone to the first Brownian zone, and then you will see this band gap more clearly, right? So why this is the case? So let's look at this Bloch's theorem. Okay, so from Bloch's theorem, we know that so this wave function inside the solid state crystal must satisfy certain requirement. So the requirement that the wave function basically can be written as a product of a plane wave and multiplied by another periodic function which has the same periodicity of the lattice, right? So now suppose we have a k prime which is outside the first Brownian zone, and then it's somewhere, anyway, it's just outside the first Brownian zone, and then it's basically shifted from a specific K point, a particular K point inside the first Brownian zone by this amount. So G is the fundamental translational vector of reciprocal lattice, and then N is an integer, right? So, and then of course this will be a K point, at nth Brownian zone, okay, something like that. And then so we can define this as a K prime. So now phi K prime will be given by U K prime, and then E K prime to R. So this is to satisfy Bloch's theorem, right? So now we substitute this K prime in here, and then of course we get K dot R, which is from this one, and then multiplied by another phase factor, which is due to this part. Then we can group this phase factor together with this one. So now we know that this part must have a periodicity of the lattice of the electrostatic potential. Why? Because this is defined, this is from the Bloch's theorem. And then of course, this part also satisfies the same condition. So this means that when R changed by one translational lattice vector, so that basically the periodicity of this one, right? Of course, so this G dot that would be multiple of 2 pi. So if it's multiple of 2 pi, and then this N is an integer, so eventually this basically is 1. So this means that this one also has a periodicity, of this one. So since this has a periodicity of lattice, and this also has a periodicity of lattice, then put together, of course, you still have a periodicity of lattice, and then basically this, just call it UKR, which has a function of periodicity, right? And then, so how do you know that this one is the wave function, is a U for electron with a state K? So, I mean, you can put in this way, since this is a wave function, this is a wave function of electron inside the crystal, right? And then this is the plane wave factor, and then this plane wave part is defined by the wave vector K. So this means that this must be the part, must be the U for the Bloch wave with the wave vector K, right? So I hope you can understand this, because this is a wave function of electron inside the crystal. And then this is the plane wave part. And then of course, these two put together must be the wave function, the periodic part of the wave function, right? Of electron with a wave vector K. So if that's the case, of course, this basically is a phi K R, and then this is phi K prime R. So you can see that this one is same as this one, okay? Okay, so this means that we can just bring this one, for example, for this one. So this one, so this part, and if we shift this parallelly, this means we don't change energy, right? Shift it parallel, we don't shift energy. And then by this, by G, 1G. So for this one-dimensional lattice, so 1G basically is 2 pi over A, because from here to here is 1G, right? So pi over A minus pi over A, so this is 2 pi over G. So you shift this one by this amount. So this basically is 1G. And then you can see that, so this part now becomes this blue part. And similarly, so this one, you shift this one to the left by G, 1G, then you get this red part. So now you have this one. This is in the first Brillouin zone, right? So this basically comes from second Brillouin zone, right? And then this one and this one in the third Brillouin zone. So we just need to shift this one by 1G, right? So now you see this one coming here, right? So this is the third Brillouin zone. So first Brillouin zone. And then this initially is third Brillouin zone, right? So you by 1G from this one. So now, so we have this one, and this one, and this one. So this together, and then you see the reduced zone representation of the band structure. So now you can see that this is the one, this is the first band, mini band, and then this is the second mini band, and then this is the third mini band. You just move on, okay? And then between each mini band, we have band gap. So here you have band gap, so very large band gap at the center, and you have a smaller band gap at the zone boundary. And then this one, you have a smaller band gap at the Brillouin zone center. And then, so this, you have a large band gap at the Brillouin zone boundary, right? So that basically, is what you will see. Okay, so once you have this, and then we can define, so what kind of material, a semiconductor, and what kind of material is a metal, right? So with this band structure. Okay, so in order to do this, and then we try to recap this Brillouin zone concept first, right? So remember, and if you have a one-dimensional lattice, so basically it's a monatomic chain sequence. So this is a monatomic chain and has a lattice spacing of A, right? So now remember when we talk about when we introduce the concept of phonon, and we try to apply the periodic boundary condition to the lattice vibration, right? And then we somehow just choose a length L. Then we see that this lattice will be repeated by this segment, and eventually you can construct a periodic lattice with infinite lengths in one dimension, right? So when we do this, and then we know that the k vector will be quantized. So this means that if you don't do this, if you don't apply this periodic boundary condition, and then you just have a continuous, you will have continuous omega q dispersion, right? And however, if you apply periodic boundary condition, it becomes quantized. So this, you can consider this as a mathematical trick to create some sort of water periodicity, and to ensure that your lattice is infinite long, right? But it will not affect the physical meaning, or will not affect the physical quantity which you are going to calculate, right? So I already explained this one. And of course, we use the same concept in when we calculate the Fermi when we evaluate the Fermi surface, right? And also the Fermi wave vector. So you realize that when we derive the Fermi wave vector, the L you choose is arbitrary. Eventually, they are cancel out. It won't affect your calculation, right? So now, so if we do this, and then the reciprocal lattice of this real lattice basically will be given by all this the red point here. So you can see that, and so this basically is one reciprocal lattice point, another reciprocal lattice point. So all this red points here, so these are reciprocal lattice points. So once you know this reciprocal lattice points, just choose any one. So as a reference, you call it center of your Brillouin zone. And then you can use this one to construct the Brillouin zone, right? So you try to find out, so what's your, sorry, I think this is a little bit confusing. I need to draw something here. I think this, okay. So what happens here that, and so your reciprocal lattice point will be this one. So this one, and then this one. So these are the reciprocal lattice points, right? Because the the lattice space in the fundamental translation vector of the reciprocal lattice should be 2 pi or A because the purity of real lattice is A, right? So these are, I forgot to put it here. So these red dots. So these red dots are basically reciprocal lattice points, right? So, okay. So once you know this, and then we can construct the first Brillouin zone. So how to construct means we choose this one and this arbitrary reciprocal lattice point, and then try to connect this one with the nearest neighbor of a reciprocal lattice point. So basically this one, and then we find a line which is bisecting, bisecting, this line segment, and then that be this one, right? And similarly for this side, so this will be nearest lattice point. And then so this is a point which bisects this line. And then so this will from here to here, and then you have the first Brillouin zone, right? And similarly, after that, you try to construct the second one, and I find out this blue region is the second Brillouin zone, and the red region is the third Brillouin zone, right? That's what I found out. And then if you look at the first Brillouin zone, the first Brillouin zone, and then you can see that, so this is the first Brillouin zone, okay? And so the first Brillouin zone will be quantized into n states of different k values. So that's because we choose this kind of periodicity, right? You can choose a different value anyway, it's arbitrary, okay? So now you can see that you have n and k states. And then each k state can accommodate 2 electrons with opposite spin, right? So this means that within the first Brillouin zone, and then you can have 2 n states for electron to occupy, okay? So you have n k states, and but 2 n electron states, electronic states. This means because each k state can be occupied by 2 electrons, right? Because electrons have different spin, okay? So it means that overall in the first Brillouin zone, you can put 2 n electrons, right? So that's what we have. Okay, so once you have this one, so now suppose you have this so-called monatomic chain, and then each atom of the monatomic chain will contribute only 1 electron. Okay, so in this case, and then you see what happens since within just right now, if you have n atoms within that monochain segment of length n, length L, right? And then so within the first Brillouin zone, and then you can have 2 n electron states. But since you only have n atoms within that line segment, so basically this one, right? So you only have n atoms, okay? So, and then each atom will contribute 1 electron. This means you only have n electrons. But the n electrons, you have 2 n states. So this means eventually you start to fill up from the lowest energy first. And then when you are only filling up to half of the first mini band, and then you use up all the electrons you have, right? So this means that the first this mini band actually is partially filled up. Okay, so in this case, and then you will have a metal. So why this is the case? So this is because that when you apply electric field, in this case, you apply electric field to this material, and so if suppose electric field is in this direction, right, and then remember this is your K, right? So electric field in this direction, and then of course the electron will move in opposite direction, right? So when electron trying to move in opposite direction, so this means that this K has to change. So you have a delta K. So now, so this means that so this electron, will move here, right? And then so this will move here, and this will move here. So this will move here. So just continue. and then we move here. So eventually, of course, you have an empty. So this part will be empty, right? So in this case, you can see that you have a current which is moving in the electric field direction. So this will be a current. So we use current densities for them, right? So this means this is a metal, okay? And then so why you can move? Because you have an empty states here, right? So that's the reason why it's a metal. So now you look at the case that if you have two electrons, so you have 2 electrons per atom, okay? So then in this case, you have a total number of electrons you have will be tau n, right? So total number of electrons tau n, and also the states available also tau n, right, in the first valence zone, right? In this case, you can see that you fill up the entire, you basically fill up the entire the first valence zone, right? So in this, once this happens, and then, for example, now you apply electric field. So in the same case, right? Even so now electric in this direction. I don't know just for now which direction we have been using, but anyway, suppose let me see. To put this, okay, put the same. So now, so if we electric field in this direction, and then of course electron will try to move in this direction, right? So now the problem that this first one cannot move. So this one cannot move. So if this one cannot move, and then so others also cannot move. So in this case, so their K cannot change. There cannot change, right? Because this is a K. Why cannot move? Because there's no empty space. So electron can only occupy the empty space. There's no empty space, they cannot move. So the only possibility is for this one to jump. So when this happens, and then what happens? This is called something like a breakdown. Why? Because the bond is broken, right? So only when this happens, and the next one can move. Otherwise, and then this one cannot move. So this means that, to move from here to here, you need a very, if the band gap is very large, say for example, if the band gap is is much larger than what the thermal energy can provide this to you, and in this case, and then you cannot move. Okay, you definitely cannot move. So this means that you have an insulator. And so if this band gap is reasonably small, say is smaller than 4 electron volt, then typically we call this a semiconductor. Of course, at low temperature, at the very low temperature is an insulator, but at the finite temperature, if your band gap is not very large, and then we do have means to bring electron from this we call valence band to this conduction band, and then other electron can move. So this is called semiconductor, right? So I hope by this very simple example, you know that why some materials are semiconductor and some materials are not. Okay, so now so this means that so in general, so a crystal can only be an insulator if the number of valence electrons in the primitive cell is an even integer. So if it's not even, and so you either have the case that is partially fill up, or you fill up the first mini band and then you move on to the second mini band. But second mini band will be partially fill up, right? So in either case, if the number of valence electrons in the primitive cell is even integer, and then you won't have any vacant states in the same mini band for electron to move. So in this case, you get an insulator, right? So and of course, if you have an overlap, so you have an overlap. So band overlap. So in this case, it may happen that instead of, so one band is completely filled up, and then you may have 2 bands which are both partially filled up. So in this case, of course, you can also have a metal, but so this kind of metal then typically is not as good as the normal metal we're talking about, for example, copper or gold or silver, right? And so semiconductor, for example, diamond, silicon, germanium, and so so each we have 2 we have, so basically 8 valence electrons per perimeter cell. That's because that for each perimeter cell, we have 2 atoms, and then each atom will contribute 4 valence electrons. So of course, this is an even number, and there's no overlap, band overlap. That's the reason why, and at a low temperature, so basically you get a semiconductor or insulator, right? So when temperature is increasing, and for example, initially if you have an insulator like this one, but if the band gap is finite, so band gap is not very high, so at a finite temperature, there's always a finite probability for electron to jump from this lower energy band to the higher energy band. So when this happens, and then you can have electric conduction. Of course, the conductivity will depend on how much electron you have at the higher energy state and how much empty states you have at the lower energy lower mini band, right? So when you have a lot of electrons at this higher energy band, and at the same time a lot of empty states, we call holes later we know, a lot of empty states and at a lower energy band, and then of course both will contribute to electric conduction. Okay, so that actually is typically so is what is happening in the semiconductor material. So now, and so this is just some sort of generic picture, and to show you what kind of material and is a semiconductor, and what kind of material is metal, and then what kind of material is something in between. Okay, so insulator, so over semiconductor, so basically at a low temperature, semiconductor is an insulator, right? So that's why you can put the semiconductor and the insulator in the same category. So this means that you can see, and so the lower energy band is completely filled up, and then the next higher energy band is completely empty, and in between is a band gap, and then there's no overlapping between the energy bands in the entire first valence zone, and then at the low temperature, carriers in the lower energy band cannot jump to the higher energy band. So in this case, and then you have an insulator or a semiconductor. And the metal is just opposite. So metal, we can see that, and so lower energy band is completely filled up, and then the next higher energy band is partially filled up. So when you apply electric field, and the electron be able to move along this k-axis, because there's an empty space, right? So electron can move to fill up the empty space, and then others will try to fill up the empty space left over by the previous electron. So eventually you have a chain of movement of electrons, so which will give you electric conduction, right? And then in between, so you can see that you have another type of material. So you have a band overlap. So basically, you can see the maximum of the lower and energy band is higher than the minimum, local minimum of the next highest energy band, right? So in this case, you can see that since electron will try to fill up the states with this lower energy first, so that's why after you reach this level, instead of continuing to fill up to the maximum of this energy band, it will fill up the local minimum of the next energy band first. So in this case, you do have free carriers here, and then you have empty states here. So this means when you apply electric field, and then so both are able to move. However, that typically electrons in this region, right, will be scattered more easily, compared to this one. And of course, electrons can also be scattered between these two energy bands. So eventually, so this will result in a higher resistivity. So it means that it's conductive, but resistivity is higher than this simple, a metal case. So this kind of material we call semi-metal, right? So if the overlap, is small, right? So of course, if the overlap is very large, and then you get, basically it's a metal, although the conductivity will not be as good as this kind of metal. Okay. So here we just list some of the resistivity of some of the typical insulators and then semi-metals. and also the so-called good metals, good conductors, right? So, and of course, glass, the mica, and the quartz. So these are very good insulators. And then, so this magnesium, bismuth, graphite. So these are metals, but you can see that the conductivity, resistivity is much higher than copper or aluminum or gold. And then graphite typically is a semi-metal, right? Also bismuth, right? So these are semi-metals. Okay. Now we still have some other metals which are shown here. For example, the resistivity of calcium, titanium, manganese, zinc, copper, and the silver and the lead. So you can see that the resistivity of these kind of metals are not very high compared to, of course, very low compared to semiconductor, but still quite high compared to, for example, copper. For example, manganese, right, is a metal. Compared to copper, you can see resistivity is much higher, right? And the calcium, right? So all this basically are determined by the electronic band structure of these materials. And so silicon, germanium, you know, these are semiconductors. So resistivity can be changed. So this we'll learn in the next few lectures, right? Some of the oxides are actually also conductive, right? So you can see resistivities actually are quite low. And of course, some of the oxides are complete insulators, for example, aluminum oxide, so zirconium oxide and titanium oxide, right? Okay, the difference between metal and semiconductor can be easily recognized in their temperature dependence of the resistivity, right? So typically for a metal, and then you can see that the resistivity high at a high temperature. So this is mainly due to phonon scattering. So it means that the high temperature lattice will vibrate very strongly. And then, so this will give you high density phonons. And then electrons will be scattered by the phonons. So this will give you the high resistivity. When you reduce the temperature to a very low temperature, and then the scattering, mainly from electron scattering with the defects, and or electron scattering. So eventually, you can see that you have finite value. So resistivity will decrease with temperature, but it won't approach zero, right? And so increasing the observation that, of course, some materials, you know that when you reduce temperature, eventually you reach a superconducting state, and then resistivity will be zero, right? And the interesting thing is that for most very good conductors at the room temperature, for example, copper, gold, and the right, and the silver. Maybe just look at the copper, okay, copper and the gold. So when you reduce temperature to even to very, very low temperature, it won't become a superconductor. And then many of the very good superconductors and at low temperature are superconductors, but at high temperature, the resistivity actually is quite high. So why this is the case? Because their conduction mechanism are actually totally different, right? So of course, you have so many different types of superconductors. We don't go to details, but you know, if you are doing material research, sometimes you find a material, you find that resistivity is quite high at the room temperature, and if you are doing, we are working on superconductors, you know that you should not exclude this as a potential superconductor, right? You only know this until you reduce the temperature and see how the resistivity will change. And semiconductor is completely different. Okay, anyway, this is the zoom up region of this region. You can see that the resistivity will only decrease, eventually saturate. Okay, so you do have a upturn somewhere here for very special situation that's called Kondo effect. If I'm doing solid state physics study, you should know that this is a phenomenon discovered by Dr. Kondo. And then so typically that will happen when you have a pure conductor, for example, copper. You dope this copper by magnetic impurities, right? And then eventually you see that when you reduce the temperature to a very low temperature, the resistivity will increase a little bit. So it's called Kondo effect, right? If it's a pure metal, you always have this kind of temperature dependence of resistivity. And the semiconductor is just opposite. So semiconductor, you know, at low temperature, basically is the insulator, right? So that's why resistivity in principle goes to infinity. And however, at a high temperature, because due to thermal agitation, and some of electrons will start to move freely, and then this will also generate vacancies, electron vacancies, which are holes, which we'll talk about later, and then both will contribute to electroconduction. So that's the reason why when you increase the temperature, and then resistivity will decrease. So this is called semiconductor, right? I already mentioned this one in the introduction when we talk about why we need a semiconductor. And so basically, if you compare metal and semiconductor, since we already talked about Fermi wavelengths, all of this, right? So so this one is already explained. So basically, metal we have a very high carrier density, and the semiconductor you have can control it. So basically, from low to high, and then you can change the carrier density. So that's very important, right? And the metal, so eventually you end up Fermi surface. So electron Fermi surface are very important. And then on the Fermi surface, electron have something called wavelength, Fermi wavelength. So Fermi wavelength is just about a few angstrom. So that's the reason why it's very difficult to realize quantum size effect or quantum confinement effect in metals. And so since you have very high carrier density, of course, it's a very good electroconductor, right? So, but it's very difficult to modulate the carrier density, or very difficult to make a device by controlling the electroconduction inside the metal. So that's the reason why. So the metal, so basically now we still use metal as a conductor, but we don't use it as a function device like a switch, or a transistor. And semiconductor is just opposite. And then, so the length scale can be quite large. So that's the reason why it's very easy to realize quantum size effect. So actually, quantum size effect is very important for optoelectronic devices based on semiconductors. And of course, in electronic devices, we can also make use of this quantum size effect. Right? And also, since the carrier density can be varied by various means, so this means that we can modulate this electroconduction very easily. And so by using electric gating effect. So that's the reason why, so all the switch and transistors still made by semiconductors. Okay, so this is the first part of lecture 3. And so we just take a break, and then after that we talk about the real semiconductors, the band structure of real semiconductors.